Hi, my name is Nagasawa-Hinck. I'm a math student at UC Berkeley, and today I will be discussing Liouville's theorem in complex analysis. So what you can expect is that I'll go through the statement and the hypotheses necessary to verify before the statement applies. We'll look at an example and a non-example so that you really get a feel for why those hypotheses are necessary. I'll go through a thorough application of the theorem and give you a really explicit proof so you can see its power. And then finally, I'll point you in the direction of some additional resources. What does Liouville's theorem say? If f of z is an entire function such that f of z is bounded for all z in the complex numbers, then f is a constant function. Well, let's remember that an entire function means that f is defined for all the complex numbers and that f is differentiable at all of those complex numbers. And what does bounded mean? Well, bounded we're really referring to magnitude. So if the magnitude of all f of z is less than or equal to m for some real number, if these two are true of this function f, then we get that f is constant. Now, this is one of the first real deviations we witness of complex analysis from real analysis because sine of x is defined for all real numbers, differentiable at all points in the real numbers, which is analogous to our idea of entire. It's also bounded, but sine of x not constant. Okay, so now if we look in the complex numbers and let's look at sine of z in complex numbers. Well, Euler's formula tells us that we can write it as e to the iz minus e to the negative iz all over 2I, which when we plug in imaginary inputs that are really, really big, this magnitude is approximated by e to the x over 2, and that's definitely not bounded. So when could we apply it? Well, if f is entire and we have that the real component of our function is bounded, then we get that f must be constant. So recall that let's think about a composition. So if we define g of z to be the exponential function e to the z, and we consider composing g with f, then we get e to the f of z. And this magnitude is going to be bounded by writing it as e to the real component multiplied by e to the I of the imaginary. Well, e to the I, again, of the imaginary is going to be like moving around the unit circle. So we're bounded by 1. And since we've shown that the real component of f of z is bounded, well, then our composition is bounded by e to the m. Again, another real number. So we have the composition of two entire functions. It's going to be entire. And we've satisfied that it's bounded. So Liouville's theorem tells us that this composition must be constant. So let's look at the derivative of the composition. We get f prime of z equals to multiplied by e to the f of z. And we know that that exponential is never 0. And if it's constant, then it has to have a derivative of 0 because from Cauchy's integral theorem, we have that if f is defined over a connected region and its derivative is 0, then it has to be constant. And so these two taken together tell us that our function f has to be constant. So what's something that has a little bit more heft or says a little bit more? Well, if f is entire and non-constant, then we're going to use Liouville's theorem to show that our image has to be dense in C. And let's recall what it means to be dense. Well, that means that every complex number z is arbitrarily close to our set. So we're going to show this by a proof by contradiction and suppose that f of z is not dense. So what that means is that there has to exist some z naught and some real number such that the disk of radius r around z naught intersected with our image is empty. And well, what does that mean if it's empty? It means that this distance between any element of our image and a z naught has to be at most r. So what we found is found a bound on this difference. And so, okay, great. What if we define g of z, kind of like we did in the last problem, as 1 over f of z minus z naught? Well, f of z is entire, and it doesn't have a singularity at Z0. So that means that G of Z is entire. And let's look up at that inequality. What if we invert it? Then we get that 1 over f of z minus z0 is less than or equal to 1 over r. Well, that describes the magnitude of G of Z. So we get that we have a bound for G of Z. Okay, so now we've verified that G of Z is entire and that it's bounded. So Liouville's theorem tells us, well, G of Z has to be constant. So there has to be some lambda in our complex numbers with G of Z equal to lambda for all Z. And G of Z is never 0, so lambda can't be 0 either. And with a little bit of algebraic manipulation, we get that f of z equals lambda plus 1 over z0. And lambda was fixed, z0 was fixed. So then that would mean that f of z has to be constant. But in our givens, we were told that f of z isn't constant. So we get a contradiction. And Liouville's theorem tells us that if f is non-constant and entire, then the image has to be dense. So if you're still curious and a little bit excited and you want to see maybe the proof of Liouville's theorem, I've linked a video, a couple extra problems where you can look at how it applies. Also, you get a little resolution on your middle school algebra class and finally get a proof of the fundamental theorem of algebra. And thank you so much for listening. I'll take questions if you have any.